Okay, in the previous section, we learned how to do the improper integrals. However, on the exam, some people forgot to include the limits when they did the improper integrals. So I am going to just say something about the one that was on the exam. And the improper integral that was on the exam was the integral. So let's look at an improper integral first. Okay, so we had, so from the exam, for module 5, we had to compute the integral from minus infinity to 0 of x e to the x dx. And most people got it right. Some people lost 3 points because they did not use the limit. So this is the limit as t approaches infinity of the integral from minus t to 0 of x e to the x dx. So now this x e to the x needs to be computed by parts. And so I like to do my by parts with the table. It's so easy, but not when you're writing that character. So on this side, if you remember, this is the derivative with respect to x of whatever you have. And this one is the integral of whatever you have dx. So I'm going to let x here and e to the x here. Derivative is 1, derivative is 0, integral is e to the x, integral is e to the x. I'm going to link these two. I'm going to link these two. I'm going to make this one positive and make that one negative. And so therefore, this now just gives me that this is the limit as t approaches infinity of the integral from minus t to 0. Up. I've already computed that. Don't need that anymore. Here I get x e to the x minus e to the x, because that's what I'm going to get. And I'm going to evaluate this from minus t to 0. So this is the limit as t approaches infinity. So now I'm going to put in 0. So the 0, the first term drops out. And then when I put in 0, I'm going to get minus 1. And then I'm going to subtract off when I put in t. So I'm going to get minus t, e to the minus t. And then I'm going to get minus e to the minus t. So now I get the limit as t approaches infinity of minus 1, then this is going to give me plus t over e to the t, and then I'm going to get plus 1 over e to the t. Okay, so now I can already see very easily that this limit is just going to be minus 1, so that's okay. And I can easily see that this limit is going to be 0. So the only one I need to figure out is the middle term. And so now that one is the limit as t approaches infinity of t over e to the t. And that is infinity over infinity. So therefore, I'm going to use L'Hopital's rule on this, which says I can take the limit as t approaches infinity of the derivative, which is 1 over e to the t. and that is now 0. So now I have shown that this limit is 0. So therefore, the whole thing is -1. It is a nice finite number. So therefore, this integral actually converges. And the answer is -1. Okay, so that's how we did infinite integrals. Indefinite integrals. And improper integrals. So now I want to introduce the actual integral test. So here is the integral test itself, and this is test number 4. Okay, so the integral test says let an be a sequence of positive terms. Suppose that I can write an can be written as f of n, where f is continuous. It's a continuous, positive, decreasing function of x for all x bigger than or equal to some n, okay, then it is necessarily true that the sum n equal to that n to infinity of an and the integral from n to infinity of f of x dx both converge or both diverge. Okay. All righty. So that's the theorem. Where does this theorem come from? Well, basically, if you're looking at a sum of terms, okay, that's basically, and you're looking at an integral is giving the area underneath the curve, which we can approximate by small rectangles. And so therefore, if I'm summing the rectangles and I can get a finite number, then I can sum I can do the integral and also get a finite value. Okay, so let's look at the sum n equals 1 to infinity of n e to the minus n squared. So I need to look at this. This is my series. Okay. Now, I can prove that the function f of x, so an is n e to the minus n squared. So my function f of x is going to be x e to the minus x squared. okay? And to show that this thing is decreasing, I just basically need to show that its derivative is negative, all right? So to show that f of x is decreasing, we already see it's continuous. We just need to show that f prime of x is negative. Okay, so therefore I have f of x is x e to the minus x squared. F prime of x, derivative of the first is 1 times e to the minus x squared. That's the derivative of the first times the second, plus the first x times the derivative of the second is e to the minus x squared. Then I have to multiply by minus 2x. So now I get e to the minus x squared, or negative x squared. And then I get 1 minus 2x. Okay? Well, e to the minus x squared is always positive. So this piece is always positive. So therefore, I would need 1 minus 2x to be less than 0. So I get 1 is less than 2x. So x is greater than a half. And so indeed, where I'm starting at n equals 1, for all x greater than a half, the function is decreasing. So that's clearly, if I start at 1, 1 is going to be decreasing. So I can use the integral test. So the integral test says, by the integral test, the sum n equals 1 to infinity of n e to the minus n squared, and the integral from 1 to infinity of x e to the minus x squared dx both converge or both diverge. So therefore, since they both converge or both diverge, let's look at this integral. So now we get the integral from 1 to infinity of x e to the minus x squared dx is the limit as t approaches infinity of the integral from 1 to t of x e to the minus x squared dx. Any questions? Y'all are awfully quiet today. I think that just means y'all are understanding it. Okay. So now I'm going to get let u equal negative x squared. So du is going to be minus 2x dx. And so therefore x dx is minus 1/2 du. And when x is equal to 1, u is equal to minus 1. And when x is equal to t, u is equal to minus t squared. So this becomes the limit as t approaches infinity of the integral from -1 to minus t squared of x dx is 1/2 du. So this is 1/2 e to the u du. So that is the limit as t approaches infinity of 1/2 e to the u evaluated from -1 to negative t squared. That's the limit as t approaches infinity of 1/2. I'm going to get e to the negative t squared minus e to the -1. I'll just throw one more step in here. The limit as t approaches infinity. So, put my 1/2 back. So I'm going to get 1/2. This looks like 1 over e to the t squared minus 1 over e. And I think I lost a negative. Yep, it's minus 1/2. And then this term, I can clearly see that term goes to 0. So I get 1 over 2e. And 1 over 2e is a very nice number. So this converges. So then that implies that the sum n equals 1 to infinity of n e to the minus n squared also converges. Now there's one important fact here, but we don't know what its sum is. We don't know to what it converges. So the integral test will tell you whether something converges or diverges, but it will not give you the sum. If a series converges or diverges, but it will not give you the sum. Okay. All right. Another example. The sum n equals 1 to infinity of 1 over n is 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus dot, 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 dot plus 1 over n plus dot, dot, dot. This series has a special name. It is called the harmonic series. Very, very important series. Okay, it has a special name. It is the harmonic series. Okay. So let's check it for convergence. Well, if I use the nth term test, the nth term test of divergence, that would see the limit as n approaches infinity of an, but that's just the limit as n approaches infinity of 1 over n, and that's 0. So therefore, the test is inconclusive. So that didn't help me. So I can't use geometric series. I can't use telescoping series. I can't use nth term test of divergence. There is a nice long way to prove it, but I just want to do it, and I'm going to do it using the integral tests. All right, so let's look at the integral from 1 to infinity of 1 over x dx. So an is 1 over n, so f of x is going to be 1 over x. Now, let's take the, we know 1 over x is decreasing. We've graphed it a million times. Okay, 1 over x just looks like this. Okay, we're only worried about positive n's and going from 1 to infinity. It's a decreasing function. You can take the derivative and get minus 1 over x squared. That's definitely negative. So this is a decreasing function. I can use the integral test. So therefore, the integral from 1 to infinity of 1 over x dx is the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. This is a nice, easy one. This is the limit as n approaches infinity. Integral of 1 over x is the natural log of the absolute value of x, evaluated from 1 to t. We don't even need the absolute value because we know we're bigger than 1. So this is the limit. And why did I get n? That should be a t. A t. Lord, please don't tell me I made that mistake back here. Let me just make sure. Nope, those are all t's. Good. Okay. So I'm going to get the natural log of t minus the natural log of 1, which is the limit as t approaches infinity of the natural log of t. And the natural log function, we also know what that looks like. Okay, that didn't do right. The natural log function increases forever. So this limit is infinity. So therefore, since the integral from 1 to infinity of 1 over x dx diverges, the sum n equals 1 to infinity of 1 over n also diverges. Okay, any questions? I'm gonna do one more. Actually, I'll go on to the P series, but I want to say something about example 3. The integral, oh, nope. This is the one we looked at earlier. The sum, n equals 1 to infinity of 1 over n squared plus 1. And so I said to you, we didn't have the tools at the time to determine whether or not this series converged or diverged. But we do now. So if an is equal to 1 over 1 plus n squared plus 1, then f of x is 1 over x squared plus 1, and f prime of x is minus 2x over x squared plus 1 quantity squared. And that is always negative if x is greater than 1. So it's a decreasing function. So let's use the integral test. So let's look at the integral from 1 to infinity of 1 over x squared plus 1 dx. So that's the limit as t approaches infinity of the integral from 1 to infinity of 1 over x squared plus 1 dx. Now we did this crazy integral before, something similar to it. This is the limit as t approaches infinity. And then when I integrate that, what do I get? What do I get? What do I get? What do I get? Hello, I hear crickets. Integral from 1 to t of 1 over x squared plus 1. I just think y'all are afraid to answer because y'all know this integral. I know you do. What is that integral?
Is it tan inverse?
Thank you, thank you. So this is the limit as t approaches infinity of the tan inverse of x evaluated between 1 and t. So that is the limit as t approaches infinity of the tan inverse of t minus the tan inverse of 1. Okay. So here, when I'm trying to find the limit of tan t approaches infinity, I'm trying to find the angle. So right here, this is asking me for the angle whose tangent is going to infinity. And this is asking me the angle whose tangent is equal to 1. So the angle whose tangent goes to infinity, we drew this before. The tangent function has an asymptote like this at minus pi over 2, and another asymptote. Are you kidding me? at pi over 2, and the tangent goes like this. So the angle whose tangent is trying to go to infinity is pi over 2. And the angle whose tangent is 1 is pi over 4. So this answer is pi over 4, and therefore it converges. So that implies that the sum n equals 1 to infinity of 1 over n squared plus 1 also converges. Okay, so before we leave here today, we're going to do the 5th test. And this is the P-series test. And so it is of the form summation n equal 1 to infinity of 1 over n to the p. Now, we already showed that this diverges. That the summation n equals 1 to infinity of 1 over n diverges. So we know it diverges when p is equal to 1. Okay, so that we know. So let's use the integral test to find out for what p it does diverge and what p it converges. So we can use the integral test to find p for which the summation n equals 1 to infinity of n to the p converges. So let's look at the integral. The integral from 1 to infinity of 1 over x to the p dx. Okay, so this is the integral from 1 to infinity of x to the negative p dx. So that is now the limit as t approaches infinity of the integral from 1 to t of x to the negative p dx. Oh, I'm tired. So that is the integral. Sorry, it's not. Is the limit as t goes to infinity of the, and then we're going to integrate that. So now we just take and we add 1 and divide. So we get x to the negative p plus 1, and then we divide by p plus 1, negative p plus 1. And we evaluate that from 1 to t. And then that gives us the limit as t approaches infinity. I'm going to take out the 1 over 1 minus p. And then I'm going to put in yeah. So now I'm going to get 1 over t. That looks sloppy. 1 over t to the p minus 1 minus 1. Okay. Now, if P is greater than 1, then P minus 1 is greater than 1. But that means that the limit as T approaches infinity of 1 over T to the P minus 1 is 0, because it's going to a positive power in the denominator. T is going to infinity. Okay. So therefore, we can say that this integral is equal to just 1 over P minus 1 if P is greater than 1. And that's a finite number. But if P is less than 1, then the limit as T goes to infinity of 1 over P minus 1 of T to the 1 minus P minus 1 is equal to infinity, and that diverges. Okay, so now we have a rule. The summation n equal 1 to infinity of 1 over n to the p converges for p greater than 1 and diverges for p less than 1. And then up here we showed it diverged for p. So we get this. So this is a very nice test. Very nice test. It has to be in the p-series form though. Summation n equal 1 to infinity, 1 over n squared converges. Summation n equal 1 to infinity of 1 over n to the 1.01 converges. Summation n equal 1 to infinity, 1 over n to the 1/2 diverges. Summation n equal 1 to infinity, 1 over n to the 0.99 diverges. It's that simple. That is the p-series test. So if p is greater than 1, converges. P is less than 1, diverges. There's nothing else to that. So now you guys know 5 tests. All right, so we started off with the geometric series. Then we did the telescoping series. Then we did the nth term test of divergence. Then we did the integral test, which says if the integral converges, the series converges. The integral diverges, the series diverges. And then the last test that we did, which is number 5, is the p-series test. It just has to look like n to the p in the denominator. And if p is greater than 1, it converges. If p is less than 1, it diverges. And that is it. Yes, Kyle.
Can you go all the way down to the bottom? I just didn't get the very last part.
No problem. You mean this?
Yes, that. Thanks.
All righty.
And then the Zoom videos will be posted so we can review the lectures and stuff like that before.
Yeah, I got to get them done. Yep, I gotta get
Appreciate
it up there, so, but yes.
Okay, I'm good. Thank you.
Any questions?